intensity of the light carrying that image varies accordingly. The photoconductor is still non-conductive and carries a uniform electrical charge. When the image reaches the surface, it affects the photoconductor like this. Light from the dark image areas carries very little energy and has almost no effect on the portions of the photoconductor it reaches. Those portions remain in a non-conductive state and stay positively charged. But light from brighter image areas, like blank white paper, carries much more energy. When this light hits the photoconductor, it causes the surface to change to a conductive state. The charge on those areas flows to ground and dissipates almost completely. In this way, the light creates an invisible electrostatic copy of the original on the photoconductor, a latent image. It has a strong charge still present where the image is dark and almost no charge left where the image is light. Since the photoconductor is charged over its entire surface, the latent image always contains some detail that's not actually part of the information being copied. It's produced from dark areas beyond the borders of the original. This usually means marks on the document cover or the complete absence of reflection that results from making a copy with the cover open. Even the edge of the original document can produce a black line on the copy. Because these non-image areas still carry a charge, the copier will treat them as if they represent something dark on the original and make them visible just like the charged areas on the latent image. This is something to avoid. A copier makes the latent image visible by coating it with a dark powder or liquid. This material can accumulate inside the machine if too much drum surface is still charged after exposure, so most copiers use something to prevent it, an erase lamp. The erase lamp is a row of LEDs that runs across the drum just past the exposure area. Based on the reproduction ratio and the size of the paper being used, the control system switches on the LEDs in specific groups, timed to shine light on the drum surface at the leading edge of the latent image, on each side, and at the trailing edge. Just as in the exposure process, light from the erase lamp dissipates the charge on the photoconductor and changes the non-image areas back to a neutral, uncharged condition. Original documents vary quite a bit. Some are much more reflective than others, depending on the type of paper and the information contained. This could cause severe fluctuations in copy quality. To compensate for the variation in originals, copiers use some type of image density control, manual, automatic, or both, to adjust the brightness of the exposure lamp. Some automatic systems work like this. Before exposing the original, the copier performs a pre-scan check. In this operation, a fiber optic cable on the first scanner passes a reflected light reading from the original to a photosensor. Low reflectance from the original indicates a darker than normal surface. This usually means colored paper, which might cause a gray background on copies. To avoid this problem, the control system adjusts the exposure lamp voltage. When the sensor detects a dark original, lamp voltage is increased a certain amount to create a brighter reflection and a balanced latent image on the photoconductor. When the original is conventional white paper, no adjustment is needed. The normal lamp voltage allows the machine to produce a clean copy. The circuit for the exposure lamp usually involves a dedicated circuit board for high voltage control elements. To switch the lamp on, the main board triggers a regulator circuit on the high voltage board. Image density information, whether from an automatic sensor or manual control, is sent to the main board, which then passes a control signal to the regulator circuit. This circuit adjusts lamp voltage to the appropriate level, and a triac switches the voltage to the exposure lamp. Since a copier's lens and scanners move to do their jobs, The machine's control system has to know where they are before and during a copy cycle. One way to keep track of their locations is to designate a point in each component's range of travel as its home position, and then monitor that point with a sensor. Photointerrupters are often used for this. Small plastic blocks with a photocell on one side and an infrared LED on the other, separated by a narrow gap. Each moving component has an actuator that enters the gap, interrupting the light from the LED when the component is at its home position. This turns off the photocell and alerts the control system accordingly. With photointerrupters suitably positioned, the control system can tell when moving components are at or away from their home positions and determine if a new copy cycle can begin. For moving the lens, additional accuracy is needed, since only through careful repositioning can the copier produce consistent enlargement and reduction. This is done with a stepper motor, which can be controlled in precisely calibrated steps. Each step is a small fraction of one revolution and can be counted by the machine's control system. The home position for the lens is typically the position for a 1-to-1 reproduction ratio. When a different ratio is selected, the control system starts the motor and moves the lens the appropriate number of steps away from the home position. This produces a copy with the desired enlargement or reduction. To return to a 1-to-1 ratio, the lens is moved back to its home position. That's the exposure process. During exposure, an image is created with reflected light, scanned with moving mirrors, and focused through a lens. The lens moves to make the image larger or smaller, while additional mirrors move to keep the image in focus. Finally, the image reaches the charged photoconductor. The light areas remove the charge from the surface, while the dark areas leave the charge alone. This creates an invisible electrical copy of the original on the photoconductor, a latent image. At this point, the machine has made an accurate copy of the original, but it's not in any usable form. Can't even see it yet. The next step in the copy process will make the image visible: development. Here's an original, and here's a copy. We've been looking at the technology that gets us from here to here. Earlier in this program, we examined the photoconductor, the material that makes electrostatic copying possible, and we've seen how the charge and exposure processes create a latent image, an invisible counterpart to the original you're trying to copy. The key word here is invisible. Just like an exposed roll of film, the latent image on the photoconductor needs to be developed. In a copier, development relies on electrical attraction and magnetism. As the latent image moves away from the exposed area, for the first time in the copy cycle, the photoconductor comes into physical contact with another component, the development unit here. Now remember, the latent image is actually a pattern of electrical charge. That's what makes the development process possible. Inside the development unit, there's a supply of material, usually black, that's known simply as developer. Sometimes it's a liquid, sometimes a powder. We're going to look at the most popular system, which uses two different dry materials combined to make what's called a two-component developer. Here's one component called carrier. It has about the same texture as sand, but the individual particles are round, like little ball bearings. Carrier is made from an iron-based material, so the particles are attracted to a magnetic object. This quality is an important aspect of the system. Carrier is not used up during the copy process. It stays in the development unit and only has to be replaced when it wears out after many thousands of copies. The other component is toner, a much finer powder than carrier. It's made from resin combined with carbon or colored pigment.
Toner isn't magnetic, but it will respond to an electrical field. Inside the development unit, toner and carrier are mixed together, and the toner gets an electrical charge that's opposite the charge of the latent image. Then a special roller brushes some toner over the photoconductor. Since opposite charges attract, the latent image attracts toner particles and becomes coated with black or whatever color toner you're using. The latent image becomes a visible image. Here's an example. Remember the charge process? We demonstrated one way that things develop a static charge, by being rubbed against something. Our demonstration earlier used this process to create a charge on a piece of acrylic plastic. There's a special name for a charge that builds up from mechanical action. It's called a triboelectric charge. You'll see in a minute what it has to do with development. Okay, imagine this cylinder is the photoconductor drum. It's sitting like this inside a copier. Somebody wanted to copy and pushed the print button. The drum began turning. It was charged here. Still turning, it was exposed here. Still turning, and now after exposure there's a latent image on the surface ready to be developed, moving down to about here. The charge on a real photoconductor is electrostatic, while the charge on the developer is triboelectric. For this demonstration, I can simulate the developing action by putting some triboelectric charge on our imaginary drum. Okay, here it is, a charged photoconductor, ready for development. By letting it attract an appropriate material, the latent image can be made to appear just like this. The drum turns, the latent image comes in contact with the development system, and what was invisible can now be seen. You see how the surface has randomly picked up these bits of paper? This is because by rubbing it, I created an even triboelectric charge on the surface. There's no detail, nothing you'd really call an image. But if I had a way to charge this surface selectively, as a copier does with its exposure system, then after development, you would have seen something like this.
As the photoconductor drum rotates, the latent image approaches the development roller. The roller's surface is coated with developer, a mix of toner and carrier. The toner carries a charge opposite that of the latent image. For our example, the latent image is positive, so the toner is negative, shown in green. Toner and carrier both start out in a neutral condition, but as they rub together inside the development unit, a triboelectric charge builds up between them. This causes toner to stick to the carrier. The development roller is magnetic, so it attracts the iron-based carrier beads, each one with a coating of toner. This forms an even layer of developer on the roller called a magnetic brush. As the roller turns, it brushes developer over the surface of the drum. Since toner has an opposite charge, it's attracted to the latent image. The toner particles are pulled away from the carrier beads onto the photoconductor. In this way, the entire latent image becomes coated with toner. Electrical attraction will hold the toner in place until it's transferred to a sheet of paper. The development system has to maintain the proper ratio of toner to carrier with a high degree of accuracy. If a copier is running with too much toner in the system, it can contaminate the inside of the machine like fine dust. To maintain copy quality and keep the machine running clean, most copiers have a system that monitors the concentration of toner in the development roller's magnetic brush and adds toner to the development unit only when the concentration falls too low. This type of system exposes and develops a small test patch on the photoconductor once about every 10 copies. A photosensor checks the density of toner on the test patch by reading how much light it reflects. The brightest reflection would be from the bare drum surface and the darkest from a very thick coating of toner. If the patch isn't dark enough, that means there's not enough toner in the development unit to provide a suitable concentration in the magnetic brush. To correct this undertoned condition, the copier's control system triggers a toner supply mechanism. It's often a special roller inside the development unit that scoops up a small amount of toner with grooves or ridges. and then drops it into the development unit. As soon as image density is dark enough, this mechanism is shut off to prevent too much toner from entering the system. This method keeps the ratio of toner to carrier balanced for an average copy, but isn't responsive enough to change image density one copy at a time. It also can't cope with the presence of toner background that can appear even with a clean original. For this level of control, the machine needs a system that responds with an immediate change in image density. Some machines adjust image density for individual copies by varying the brightness of the exposure lamp, as mentioned in the last section. Image density can also be controlled by a special electrical system that works in conjunction with the development unit. It's called the bias circuit, and it works like this. During development, toner is attracted to the latent image because they have opposite charges, usually negative toner and positive latent image. Imagine what would happen if the development roller had a stronger positive charge than the latent image. The toner would have a stronger attraction to the roller than to the drum and wouldn't leave the magnetic brush. That's how the bias circuit works. In response to information from manual or automatic image density controls, the copier's main board sends a bias control signal to a high-voltage power pack. The power pack then produces a bias voltage that corresponds directly to the control signal. This voltage is applied to the outside of the development roller during the entire copy cycle. It creates enough electrical attraction on the roller to hold back a certain amount of toner during development. To produce a lighter copy, the main board increases the bias voltage to hold back even more toner. This reduces the amount that's attracted to the latent image, resulting in a relatively thin deposit of toner on the drum. For a darker copy, the main board lowers the bias voltage, so very little toner is held back on the development roller. The result, a greater thickness of toner on the latent image and a darker copy. Inside the toner supply, there's often an agitator to keep the particles from clumping together. Here's an agitator in the development unit. It mixes newly added toner with the existing supply of carrier to create and distribute the triboelectric charge. This is a paddle roller. It feeds the toner and carrier mixture to the development roller. Almost touching the development roller is the doctor blade. It determines the height of the magnetic brush by scraping off excess developer as the roller turns. In a desktop copier, the moving parts in the development system are driven from the main motor by a system of belts, gears, or both. Typically, motor drive is transmitted to one gear on the back of the development unit. This gear engages others on the unit and transmits appropriate rates of rotation to all the moving parts in the system. With development, we passed a new milestone in the process, a visible copy of the original. The key elements are the toner and carrier. They're mixed together in the development unit to make a charged ferromagnetic developer, which is picked up by a magnetic roller and brushed onto the photoconductor. The toner is attracted to the latent image because of its opposite charge. Electronic and mechanical subsystems control toner supply, developer mixing, and image density. All that brings us to right about here. We have an image, but before it can become usable copy, we have to get a sheet of paper into the picture. And that's what happens in the next step in the process, paper feed. When people say, "I'll send you a copy," what they usually mean is they'll send you some written information on a piece of this stuff, paper. For centuries, paper has been the vehicle for carrying information from one place to another. And in spite of all the electronic sophistication in today's office automation systems, there's still nothing quite as convenient as something you can fold up and put in your pocket. In the last section,
we saw how the latent image becomes a visible toner image through the action of the development process here. The toner is now in place on the drum, ready to be moved to a sheet of paper. But first, we have to feed the paper into the copier. For copier applications, a paper feed system has to take care of three separate functions: transport, separation, and registration.
Transport is the most obvious of the three. Paper has to move through the copier at the right speed and with the right timing. Paper separation is a requirement for any sheet-fed copier. Since the machine takes paper from a stack of possibly thousands of sheets, it needs a way to make sure only one sheet is fed for each copy cycle. Paper registration is a matter of making sure the sheet is properly lined up with the latent image. The exposure system guarantees that the image is straight on the drum. A registration mechanism guarantees that each sheet of paper is straight when it meets the latent image, so a finished copy shows the same alignment as the original.
Copiers manage paper transport with components that are simple and reliable: rubber belts or rollers. Rubber is an unusual material. It grabs onto other surfaces so well because of friction and flexibility. A sheet of paper is not perfectly smooth. It's pressed out of lots of fibers. And as you can see in this close-up photo, it has many irregularities on the surface. If you try to grab this surface with something hard, like metal, you'd run into a few problems, because most of the surface is actually recessed below the top fibers. To move paper effectively, you need something that can mold itself to the irregular surface and create a more secure grip, like rubber. Even this small rubber eraser grabs the paper very securely and moves it wherever it needs to go. There's another advantage to rubber. With a little pressure, it flattens slightly, and the area of contact between the roller and paper increases even further. Okay, now that you know how rollers move paper around, let's look at how they're used for more specific jobs, like separation. Remember, paper separation is the process of pulling a single sheet from the supply to avoid a multiple feed.
One separation method uses a cork pad mounted under the first feed roller. The pad is positioned so that a sheet of paper from the supply must pass over it before entering the copier. When the feed roller starts pulling the top sheet into the machine, sometimes the sheet underneath sticks to it. This can happen simply from the friction between the two sheets. The friction between the bottom sheet of paper and the cork pad is greater than the friction between the two sheets of paper, so the pad holds the bottom sheet back. Only the top sheet feeds into the copier. The bottom one will feed on the next copy cycle. Another separation mechanism uses a pair of rollers. The top roller is coupled directly to the drive system and is always driven forward. The bottom roller is driven in reverse, but through a clutch mechanism that lets it turn forward if enough force is applied. Here's how it prevents multiple feeds. If the feed roller picks up a single sheet from the supply, forward rotation is transmitted through the paper to the bottom roller. The clutch releases and the bottom roller turns forward as well. But if two sheets are picked up, the friction between them isn't strong enough to force the bottom roller to rotate forward. It reverses. This action separates the top sheet of paper and prevents the bottom one from feeding.
Okay, we've covered the basics of transport and separation. The next step is paper registration to prevent skewed images on copies like this. Most copiers use a pair of registration rollers mounted just past the feed rollers. The machine's timing is set so the registration rollers stop just before a sheet of paper hits them, even though the feed rollers are still turning, pushing the sheet forward.
This forces the sheet to buckle slightly on contact and align its leading edge with the rollers. The sheet is now square in the paper path, ready to receive an image. In most copiers, the drive for paper feed components comes from the main motor and is transmitted to each roller by a system of belts and gears. Since feed rollers have to supply paper according to the precise timing of a copy cycle, They're usually driven through some kind of clutch.
A clutch is a type of mechanical link between two different assemblies that can make them engage or disengage as required. Most of us are familiar with the clutch in a car. It provides the link between the engine and transmission. In a paper feed system, clutches link drive gears to rollers. Motor drive can be passed to a roller or taken away, so the rollers start or stop turning as necessary. The pieces making up a clutch are designed so that one side can be turning while the other side is stationary. When it's time to engage a roller, an external mechanism causes both sides of the clutch to lock together and transmit motor drive as if it were a solid piece. This is a spring clutch. It's basically a tightly coiled spring surrounded by this sleeve. Inside the spring are two drive pieces. One supplies rotation from the copier's motor, while the other transmits that drive to a roller. Under normal circumstances, the spring grips both pieces very tightly, so both sides of the clutch turn as one unit. To release the clutch, an actuator forces one side of the spring to expand. It moves away from the drive piece inside, so motor drive is removed and the roller stops turning. A spring clutch needs some type of electronic control, and that's usually a solenoid, a type of electromagnetic actuator. A solenoid is very simple. It's a hollow electromagnet with a metal plunger partially inserted inside. When power is applied to the magnet, it creates a strong magnetic field. This field grabs hold of the metal plunger and pulls it all the way inside. If something is attached to the plunger, it gets pulled too. There's another type of clutch that's sort of a clutch and solenoid in one unit, a magnetic clutch. It uses two plates, one driven and one idle, something like the clutch in a car. To activate a roller, the copier energizes the electromagnet, which pulls the two plates together. Now turning like a solid piece, the clutch transmits drive through the center shaft and onto whatever component needs turning.
By activating and releasing magnetic clutches and solenoids, the copier's control system can start and stop the paper feed rollers very precisely. This sort of accurate control is possible not only because of clutches and solenoids, but also because of sensors in the paper path. Paper path sensors are often hybrids with mechanical and photoelectric components. Many use a small actuator lever, which every passing sheet pushes down, raising the lower portion out of a photointerrupter. They're positioned to let the control system know when a sheet of paper has reached certain key locations, so that other systems can be activated according to the proper timing. If a sensor detects that a sheet has remained in one spot for too long, the control system knows there's a problem and indicates a misfeed. Other sensors tell the control system what size paper is being used. Sometimes they detect the position of adjustable fences in the paper supply. As the fences are adjusted for a certain width and length of paper, a corresponding sensor is triggered. In copiers that use removable paper cassettes, a group of switches detects the configuration of special tabs or notches on the cassette. Each paper cassette will activate only certain switches in the group. The resulting combination of open and closed switches corresponds to a specific paper size. The electronics controlling a paper feed system are technically simple, but can become complex simply from the number of elements involved. A basic desktop copier has at least 3 sensors in the paper path: paper end, registration, and exit. The same machine might have 2 solenoids controlling paper transport on the feed and registration rollers. Electronically, the arrangement of these components is very straightforward. Sensors bring information to the main board, and the appropriate control devices carry out the instructions. The paper feed system for a large copier with a high-speed document feeder and sorter is much more complex. It might have dozens of sensors and solenoids, each sensor independently monitored, each solenoid individually controlled.
This complexity facilitates high performance and also helps the operator troubleshoot problems in the paper path. While the technology of the paper feed system is by no means unique to electrostatic copiers, it's still a vital part of the copy process. Paper feed systems rely on rubber belts and rollers to grab sheets of paper one at a time and feed them through the copier. Other rollers, or friction pads, handle paper separation and registration. Sensors in the paper path enable the control system to maintain the correct timing during a copy cycle, monitor paper size, and detect misfeeds. At this point in the copy cycle, a toner image has been created on the photoconductor, and a sheet of paper is on its way through the feed system. The next process brings the paper and toner together. It happens right here. We'll cover it in the next section on transfer and separation. Up to now in the copy process, all we have is a blank sheet of paper moving into the machine and an image of the original in the form of a thin layer of toner on the photoconductor. But the paper and the image are in two different places. Two almost simultaneous processes take place next. The toner image is transferred to the paper, and the paper is separated from the photoconductor so it can move through the rest of the machine. At this point, the paper is about here, moving toward the drum, and the developed image is on the photoconductor, approaching the transfer and separation corona units here. These coronas are very similar to the charge corona, metal housings, each with a thin wire running down the center. Like the charge process, transfer and separation rely on the action of electrical fields produced by these corona units. One field pulls the toner onto the paper, and a second field pulls the paper away from the drum. The electrical attraction created during transfer is similar to the effect of competing magnetic fields, the kind of thing you see in the motion of a compass needle. A compass works because of a weak magnetic attraction. A small magnet in here reacts to a very big magnet, the Earth, and is always attracted to magnetic north. But if I bring another magnet into this picture, things begin to change. The Earth's magnetic field may be large, but it's not very strong. Over short distances, this one is much stronger. When it's brought near the compass, there's no contest. The stronger magnet wins, and the needle is pulled away from magnetic north. Here's how this type of relationship applies to the transfer process. Imagine this as a cross-section of a photoconductor drum, and this thin magnetic strip on the edge is the latent image. Since we're at a point after development, the latent image is coated with a layer of toner held in place by electrical attraction. These ball bearings represent the toner. After development, the drum keeps turning, and the toner on the latent image is brought near the transfer corona. You can see what's going to happen in this model. It's another case of a strong attraction encountering a weaker one. In a copier, the transfer corona creates an electrical charge stronger than the latent image. The result, when the drum turns past the transfer corona, the toner is attracted away from the photoconductor. There's one other element, paper. The paper feed system is timed so that just as the developed image reaches the transfer area, a sheet of paper is being pushed up against the drum. It happens like this.
After development, the drum's rotation brings the image toward the transfer area. The image now has two components, the latent image, defined only by electrical charge, and the visible toner image, held in place on the photoconductor by electrical attraction. In response to a high DC voltage, the transfer corona generates a positive electrical field around the corona wire. The field spreads out, carrying a positive charge toward the drum. A sheet of paper enters the transfer area. In a real copier, the paper moves at exactly the same speed as the drum and is pushed into direct contact with the surface. The gap shown here is only for illustration. Once the paper is over the transfer corona, it receives the positive charge, a stronger charge than the one holding the toner to the photoconductor. the stronger charge wins. Toner is attracted away from the latent image onto the paper. The charge on the paper holds the sheet flat against the photoconductor to prevent the image from smearing. After transfer, paper and photoconductor move over the separation corona. This corona wire is supplied with an AC voltage. It produces an oscillating electrical field which breaks the attraction between photoconductor and paper. With the force of attraction neutralized, the paper's own stiffness usually separates it from the photoconductor, though curled or unusually thin paper may continue to stick. Pick-off pawls provide a mechanical backup for electrical separation. These small, sharp fingers ride against the photoconductor and strip off any paper not separated by the corona. We finally have something that looks like a copy, though not yet a permanent one. But after transfer and separation, there's enough electrical attraction present to hold the toner in place until it's bonded to the paper. For successful transfer to take place, the electrical charges on the drum, toner, and paper must be suitably balanced. If there's too much charge on the drum, the attraction between latent image and toner is too strong for the corona to overcome, and the toner won't transfer completely. Rather than reducing drum charge, some copiers avoid this problem by using a pre-transfer lamp, positioned close to the photoconductor between the transfer corona and the development unit. Light from the pre-transfer lamp reduces the latent image charge and therefore weakens its attraction. Not enough to cause the toner to drop off, but enough to assure an effective transfer. Reducing the drum charge also prevents toner particles from being attracted back to the drum during separation. The circuits driving the transfer and separation coronas are virtually identical to that used for the charge process. And in some copiers, the transfer and charge coronas share the same power pack. The separation corona differs in that it gets an AC voltage. So in some machines, a separate power pack is required.
The copy cycle is almost finished. At this point, the original image and a sheet of paper have finally been brought together. Using an electrical attraction stronger than the latent image, the transfer corona pulls the toner from the photoconductor to the paper. The separation corona then neutralizes some of the charge on the paper, enabling the paper's own stiffness to pull it away from the drum. If separation isn't complete, pick-off pawls provide a mechanical means to strip the sheet from the drum surface and guide it back into the paper path. Now we have this. A copy, a visible image of the original on a sheet of paper, but it's not quite ready to send out with the annual report. The image is supported by paper, but not attached to it. To make the copy permanent, this toner-paper combination has to go through one more process. We'll cover it in the next section, fusing. If you want to see how something can be permanently bonded to a surface, this is the kind of hardware to examine. It uses exactly the right technology for the job. In this section of the program, we're going to look at some very similar technology that's used inside a copier. In the last process, toner was transferred from the latent image to a sheet of paper, and then the paper and toner together were separated from the photoconductor drum. That happened right here in the transfer area. At this point, the original image is on the paper, but it's held in place only by a relatively weak electrical charge. To turn this into a usable, permanent copy, the toner must be fixed in place on the paper. That happens right here in the fusing system. After separation, the paper moves away from the drum over to this point, where it passes between two rollers. The rollers press together, and the top one is heated. Remember, toner is made from a type of resin. It melts at about 180 degrees Celsius. So with this combination of heat and pressure, the toner is both melted and pushed into the paper. The combination makes an excellent bond. It happens like this. For the purpose of our demonstration, Here's a sheet of paper with a toner image on